Okay.
Wonderful. Well, welcome everybody. Welcome to Cloud Native at Scale. We're a meetup community based in San Francisco, and we talk about all things cloud native. And cloud native isn't just about how we deploy applications, it's also about how we design them. And that's what we're going to talk about today. One of those key choices is about how a distributed system, how the components of a distributed system interact with each other. And so request response-based protocols are everywhere, but the industry is also adopting event-driven approaches, and those offer some compelling advantages. We're going to cover that in today's talk and talk about some event-driven patterns to scale in real-world systems serving tens of millions of users, and we'll give you hopefully some interesting advice about how to make your applications more reliable and dynamically scalable. We'll introduce our speaker in a second, a couple sort of block and tackle administrative items. First of all, you should know who I am. I'm Daniel Cohen. I'm one of the organizers. We also have Josh Hurst on the line as well. I'll be hosting the discussion today. My day job is Director of Customer Success at Styra. If you don't know us, we're the founders and maintainers of Open Policy Agent. That's a graduated project at CNCF. I've had sales engineering roles at all sorts of companies like AppDynamics and DataStax, and I was also in at JP Morgan as a VP of Global Technology some years ago in what honestly feels like another life. I'm also going to mute my phone, which is on D&D and yet somehow is still making noise. We don't like that. All right. I'll also give a shout out to our next event. So that is Wednesday, May 26th with Pierre-Alexandre Lacerte. He's a senior principal software engineer at Upgrade, and he's going to be talking about shared components in a cloud native world. As Josh mentioned, please do join our meetup. You'll be able to get all of the notifications and sign up for all the events through that. All right, now enough of all the administration stuff. I want to introduce Melinda. She is a co-founder at Eggy, a stealth startup where she's working on cloud native systems to support people who want to build the next phase of computing. Previously, she was the director of foundation engineering at VSCO, where she helped the company migrate from a PHP monolith to a cloud native distributed system running on some of my favorite technologies like Go, Kafka, and Kubernetes, serving tens of millions of users in pursuit of artistic exploration outside of ad-based incentive structures. Prior to VSCO, she worked in a bunch of cool fields like synthetic biology, computational neuroscience, and the aerospace industry. So that is the end of me for now. We're going to turn it over to Melinda. I guess one more administrative item I almost forgot. We're going to hold on to questions for the end. So we have a Q&A function in the chat. Please stick your questions in there, and we'll take the best of the bunch, and we'll be able to pose those to Melinda at the end. So thank you for your patience while we do this, and Melinda, the floor is yours.
Thanks so much for that, Daniel. Can you hear me okay, by the way? You know, it's a Zoom.
We hear you loud and clear. Yeah.
Sweet. So hi, everyone. I'm Melinda, and I'm here to talk about our favorite thing, cloud native distributed systems. Let's see if I can get this screen share to work. Screen, is it sharing?
Yes, it is. You're good to go.
Sweet. So yeah, as Daniel mentioned, I'm going to start with some slides. Then I will show a live demo of a request response architecture and how we can move it to an event-driven one. And then we'll close with Q&A or just chatting about what is on all of your minds. After the talk, I am going to post these slides, a link to the code for the demo, and other notes to this URL here at eggybits.com. And as Daniel mentioned, I work for Eggy, where we love cloud native distributed systems. Spent time at Visco and some other places before that. Hi, Shruti. So if you're writing software that touches the internet today, there's no getting around it. You're building a distributed system. And what that means is that some of your software is running in a mobile device, maybe some parts of your software are running in a web browser, some parts are running on the server, probably many parts are running on many servers. And all of these parts are calling each other over a network, which may or may not be working at any point. It might be running out of batteries. I might have dropped the computer, might have an exploded hard drive. But even in this environment, your software is expected to stay up and running perfectly, even though any of its parts might be gone, which is difficult. cloud native software is inherently distributed, and distributed systems are just difficult to design, to build, to understand, and to operate. But that's why our jobs are fun. When we build our systems, we're usually designing for three main concerns. One, reliability, like how we can make sure that the system continues to work correctly, performantly, even if there's a hardware fault, a software fault, or human error sometimes. Scalability, how to make sure we have reasonable ways of dealing with our systems growing, whether that's in data, compute, or team size. And maintainability, like how do we make sure that all of the different people that are definitely going to be working on our app, on our system over time, can understand and work on it productively. But one overarching concern about all of this is how we can keep complexity under control. Like when we start building something, it can be simple, it can be delightful, it can be clean, but as our projects get bigger, they often become complex and difficult to understand, like this. And this complexity slows down everybody who needs to work on the system. We get tangled dependencies, hacks, special cases to work around problems, an explosion in the state space. You know, you've seen all of these things, I'm sure. And one way that we as an industry have tried to manage this complexity is by breaking our software down into independently deployable services, which we call microservices, right? This has many advantages. Services can be worked on in parallel by different teams or different people. Each service can focus on a specific domain. And together, that gives us a lot more flexibility than a monolith, in theory, in how we can solve larger problems. But that's only true if we decompose our software in a careful way and use patterns that fit the specific business context that we are working in. For example, if we aren't careful, we could end up with software that is still tightly coupled, but now has an unreliable network between every piece of business logic, and is hard to deploy, and is basically impossible here to debug. Okay, so why is this, and how can we avoid that? As mentioned, one key property of our software architecture is how our microservices interact with each other. Our software, if it's decomposed, only works if multiple services work together. And the default way that we do interaction nowadays is with request response, using synchronous network calls. So in this model, we basically try to make requests to a remote network service look like calling a function in our programming language within the same process. Which seems really convenient at first, but seeing remote calls as function calls is fundamentally a flawed premise, because a network request is just not a function call. It's really different. A local function call is predictable and either succeeds or fails, depending on parameters that are totally within your control, right? But a network request is unpredictable. It could return successfully, albeit much more slowly than a function call. It could return successfully, but way more slowly. The network could be congested, or the remote service could be overloaded, so it might take 5 minutes or 20 seconds to do the exact same thing as the thing that returned in 150 milliseconds. The request or response could get lost due to a network problem. And if you don't get a response from a remote service, you basically have no way of knowing whether the request got through or not. Maybe the requests are actually getting through and only the responses are getting lost. So it's probably not safe for you to retry it unless you've built in a mechanism for deduplication. But the cloud is just a rough environment to be in. It's really, really different from a single computer. And because of this, our distributed software, when it interacts using request response, can be incredibly difficult to reason about. Imagine that you have on the order of hundreds or thousands of services communicating to each other in a point-to-point way, how many different point-to-point connections that might be. And that's what large distributed service architectures that use request response often look like. Like this, for example, is Netflix's architecture around 2015 from a reInvent talk at the time. It's about, I think, 850 microservices at the time. It shows a network of their services and the synchronous runtime dependencies on every services, on other services. And This representation is sometimes known as a Death Star diagram. You can see that as the number of services grows over time, the number of synchronous interactions grows with them somewhere between linearly and quadratically. And if you zoom into any one service, this, for example, is the call graph for a single Netflix service from that same talk. I thought this was funny, the list of movies service, or LOLOMO. These are all the services that the LOLOMO service has to talk to in order to return a response. And you can see that this one service depends on so many other ones, and any of these N dependencies being down can cause availability issues for our one service. And apart from just availability, we get latency, which grows with the depth of this dependency graph. We probably need to coordinate read times between which of these is querying the data store to make sure you're not reading an old piece of data. We're probably going to find it extremely difficult to reason about the state of the system at any point in time. There's just a lot going on, and this is just one call. And so one solution to this availability problem, discussed in depth in this paper here from Google, Calculus, is just to make sure that your individual services have significantly higher SLAs than what you need your system as a whole to have. So if you need 99.99% availability, maybe you need 5 or 6 nines in your downstream services, which, good if you can get it. Not all of us are Google. But you can also do things, and we've built these tools as an industry, like make automatic request retries when you don't get a response back with back pressure. You can add caching between clients and servers. You can have multiple redundant copies of services that can take requests when one copy is broken with live and readiness checks to make sure we're getting the live ones. We need dynamic service discovery, load balancing, circuit breaking in order to make all of this possible. Different kind of traffic control mechanisms. We have service meshes now, like Linkerd and Istio, to make all of this more transparent to the user. Distributed tracing, of course. I mean, these are all standard cloud native patterns, but these are standard patterns because trusting request response to work in a hostile environment like the cloud is inherently risky. And so much of the mindshare in the microservices landscape, the libraries, the tooling, the documentation, assumes this model of services calling each other synchronously. And I think it's a little unfortunate that we so often conflate the core values and goals of microservices with a specific model for their implementation. Request response isn't what microservices are, really. This is also a hostile environment. But what if instead of having to patch these solutions for resilience on top of request response, which as we noted has fundamental flaws, we could change the problem to a simpler one and try to just not bind our services together as much with synchronous ties. And as an analogy, I think the request response model really matches our sequential imperative programming model of making in-place state changes on a single computer. We've seen that that imperative model isn't perfectly suited for our distributed environment, but another programming style might match more closely. Functional programming in this analogy. Functional programming describes behavior in terms of the immutable input and output values of pure functions, not in terms of mutating objects in place. And we've seen in the last few years how thinking about things in this more functional way helps in other parts of the stack. On the web, for example, we've had reactive frameworks like React and Redux and Vue, Elm before that almost everyone has shifted to after seeing how they can simplify things. On mobile, the new generation of UI frameworks on both iOS and Android is functional and reactive. While Combine on iOS more recently. And on the infrastructure side, we've seen how declarative APIs like Kubernetes and infrastructure as code tools like Terraform have made things so much easier to reason about, and GitOps promises to take that further. But we're still early in adopting this in backend application development. What would it look like if we did extend the functional programming analogy to microservices architecture? Well, it's basically event-driven architecture, like functional programming. It lets us know consistently the state of the system as long as we know its input events. So there are a lot of different definitions of what could be called an event-driven system, but really the common thing is that the thing that triggers code execution in an event-driven system doesn't wait for any response, it just sends it and then forgets about it. So in this diagram on the left, there's a request and a response. When a request is received, the receiving server has to return some type of response to the client. Both the client and the server have to be alive, well, and focused on each other in order for this to work. But on the other hand, on the right, there's an event-driven service. The service that consumes an event does something with it, yes, but it does not have to send any response to the thing that originally created the event that triggered it. Only this service has to be alive for this code to be run. It doesn't depend on other services being there. It's not coupled to the thing that produced the event. It doesn't have to know about that producer at all. And the way that this usually looks in practice is that we use a message broker or distributed log to store these events. These days, this is usually Kafka or Kinesis. And the event partitioned across a horizontally scalable cluster. And each of our services can either consume from one or more topics, produce to one or more topics, do both, do neither. And we'll see this in a working example in a bit. But why is this better? It's a really different way of having programs interact. And if we're going to make this change, we better have some really good reasons. And I think the biggest reason is the decoupling and easy composability that this gives us around our business logic. By getting rid of these point-to-point synchronous flows, our system can become much simpler. Instead of having to work to add things and having that work scale quadratically, or almost so, because each new thing has to be hooked up to every existing thing, it becomes a much simpler task to just plug new services in or change services that are there. We can break these long chains of blocking commands where one piece being down at any given time means that all of these are unavailable. And if we zoom out then to a whole organization, these design principles let us build composable systems really at a large scale. So in a large org, different teams can run independently. They can design and build services that consume from topics or produce to topics. Since any topic can have any number of independent consumers, no coordination is required to set up a new consumer. And they can be deployed at will, built with different technologies, different languages, different data stores, et cetera. Each team can focus on making their particular part of the system do its job well. And as a real life example, this is how this worked at Visco. Visco is a photo and video sharing consumer platform, hi Shruti, mostly used by Gen Z. Users have their own profile. They can follow each other users and get their content in their feed. It's a social network, but no ads. What happens if a user follows another user? Well, the first thing that happens here is they hit a synchronous follow service, which then tries to get that information into this distributed log, Kafka, as soon as possible. And once it's there, it can be used for many things, right? It can get consumed by a feed fan out worker, so the follower can get the followee's posts injected into their feed. It gets consumed by the push notification pipeline, so the followee can see they've gotten a new follower, and so on and so on. And the key is that you can really keep on plugging more consumers without affecting the original follow service, right? You can add monitoring, so you can see if the rate of follows goes way down and business metrics might be messed up because we shipped some weird version of the app, or if it goes way up, if something strange is happening. We can add an abuse prevention mechanism in case something strange is happening. You can add analytics in case you need to make a report to Wall Street and so on. All of these systems can be developed independently and connected and composed in a way that is and feels robust. Another side benefit is that you get asynchronous flows for free. We don't have to, like we used to, do a bunch of orchestration to set up batch jobs with like Airflow or something. If we handle the real-time case with events, we can do offline jobs by default. And this functional composition makes things easier to trace as well. We get a central immutable saved journal of every interaction and its inputs and outputs. So we can go back and see exactly where something failed. In order to get this with request response, we'd have to invest a ton in a full distributed tracing system. And even then, we might not see where latencies are being hidden. Another reason why event-driven systems are helpful is that they can provide scale by default and make some of the patterns we talked about for resilience in request response service architectures unnecessary. So these were some of the things we talked about earlier. The distributed log really acts as a buffer. If recipients are unavailable or overloaded, it will automatically redeliver messages to processes crash. So this makes these retries less necessary. The log avoids the sender needing to know the IP address and port number of the recipient, which is particularly useful in the cloud when computers come up and down. So we don't need as much complex service discovery and load balancing. And we talked about distributed tracing earlier. A third thing is that there's something called, I guess, polyglot persistence nowadays, where we all use lots of different kinds of databases. There's no single one-size-fits-all database anymore that's able to fit all the different access patterns efficiently. For example, you might need users to perform a keyword search on a data set. And so you need a full text search index service like Elasticsearch. You might need a specialized database like a scientific or graph database to do specialized data structure traversals or filters or something like that. You might have a data warehouse for business analytics where you need a column-oriented storage engine or something like that to do queries performantly. When new data gets written, like how do you make sure that it ends up in all the right places, right? If something goes wrong, how do you recover? What if you write to one of these things and not the other? And so one thing, I guess the way that we used to do this is that we would write to all of the databases from one microservice, from one service, one synchronous service. So dual writes or triple or quadruple writes, whatever. But we've seen how that's fragile and also how it's theoretically impossible to make dual writes consistent without distributed transactions. Like you can't really guarantee that a write that goes to MySQL and also Mongo will write to both places or neither. So instead, one solution is to use event-driven systems to do what is called change data capture. This is an old idea where we let an application subscribe to a stream of everything that's written to a database, and then we can use that stream to do these things: update search indexes, invalidate caches, create snapshots, and so on. There are open source libraries for this now. There's Kafka, there's Debezium, which uses Kafka Connect. And increasingly, databases are starting to provide this sort of a stream as a first-class interface. Mongo does that, for example, now. But at Visco, because we started doing this back in 2016, before this was really a thing in the industry, we had our own version. And so if we go back to the follows use case, the way that that event gets into the distributed log in the first place is that the follows service writes to an online transactional database, say something like MySQL or MongoDB, and then our change data capture service writes every change to the distributed log where any number of consumers can do whatever they want with it. This ends up actually being a nice way to migrate off the monolith. That helped us. You can let the monolith keep doing the initial database write and suck those events into your event store with database change capture, and then pull out all of the reads from your monolith, plus all of the extra stuff that the monolith does for every write into composable workers, and then eventually kill the write worker, kill the write from the monolith. And as a side benefit to this, this helps us fix one of the most common things that catches us in microservice architecture, where we do have a bunch of independently deployable services, but they all share a single database. We usually would rather have our data not be this coupled, but it's hard to unbundle it. And change data capture makes it much easier. One more thing, I mean, we also can save much richer data with event-driven systems if we want to. Writing data as a log can really produce better quality data by default than if we update a database directly. And that really has, more to do with the way that we think about what an event is. So for example, if someone adds an item to their shopping cart I'm buying furniture, and then removes it again, those add and delete actions have informational value. If we delete that information from the database, when a customer removes an item from the cart, we've just thrown away information that might have been valuable for analytics and recommendation systems, right? And this approach, where we are storing each fact, each action that's happening in our system as an immutable fact, is usually given the name event sourcing, which comes originally from the domain-driven design community. Kind of like change data capture, event sourcing involves saving all changes to the application state as a log of change events. But instead of having something where part of the application is allowed to use the database in a mutable way and update and delete records as it pleases, in event sourcing, our application logic is explicitly built on the basis of immutable events. So the event store is append only. Usually you can't update or delete anything. And you derive the current state of the world from the stream of events. So you can imagine say, a version control system like Git, where instead of storing the actual files, imagine we stored only the diffs from the beginning of time. And then to get to a copy of your current working tree, you would basically like aggregate over all the diffs over time. That's kind of like how event sourcing systems are. In a fully event source system, the current state is derived, which is valid. I mean, both of these approaches are valid. This and the mutable version, they come with slightly different but regardless of which one we use, the important thing is to save facts as they are observed into an event log. And as a bonus, I mean, this falls out of all of the other reasons, but because I love machine learning, this turns out to be really good for machine learning. There's this idea of software 2.0, which is that increasingly we're going to want to plug machine learnable programs into different parts of our software systems, where we can get better results by learning something than by hand coding a program. Like, let's say we want to tune a database index with a model here, or decide whether this request is from a legitimate actor over there. And inserting ML like this will really just not be tractable if we do this in a point-to-point request response way. Like, our software will become totally incomprehensible. But if we've already switched to using an event-driven system, where the pluggable data integration is already there for us, adding ML becomes much less painful. That said, there are some things to watch out for with this. The biggest one is concurrency management. If we have distributed data management, how do you make sure that you read your writes, or you read all the implications of your writes? We don't really have time to go into this because it's a deep theoretical issue, but that Martin Kleppmann paper goes into it in a lot of depth. I'll link it later. Request response doesn't really solve this issue either, but I mean, we should. You do have to be thoughtful about your schemas, how you choose to structure your event data. Since your events are now your programming interface for all other actors, you have to handle backward and forward compatibility with them, just like you would with an API. Empirically, I found this less work than versioning request response APIs, but it's something to think about. There are mature systems like Protobuf and Avro for this that are quite good. Just, don't try hand rolling something on top of JSON for this. Privacy. With GDPR, with a lot of privacy concerns, because event systems make it easier to distribute our data and have things be more modular, we now have to think about how we can delete things that need to be deleted. Event-driven systems do have nice mechanisms for this, but it is something that we need to think about. But the biggest gotcha is, although it's becoming less and less true, event-driven interactions are not the norm, right? So there are just fewer libraries and tools and blog posts and example repos about this than request response architectures right now. But running Kubernetes or using infrastructure as code wasn't the default a few years ago either. So I mean, we've seen how the industry moving to these things has made our lives easier. So I posit that we'll see more and more of these things as we go forward. Okay, I will stop talking now and try to show you some code, if that's okay, if we still have time. Yeah?
We certainly do. Go for it.
Let's see if this can work, maybe. Oh yeah, it's a breakfast app. There's some breakfast, yeah. All right, so we are going to run a breakfast delivery app, a breakfast delivery service, no worker exploitation here. First on request response microservices, and then on event-driven microservices, and we'll see how that changes, see the difference in behavior. So please bear with me if this is laggy. I will try to do my best with the screen share. So the idea is that it will first, let's hide the app because that's distracting. Maybe it's only distracting to me. What we would like to do is start with a version of the service that is like this. So the web app calls an order service. This web client will call our order service, and on getting the request, the order service will call our payment service and our delivery service synchronously. Thank you to shout out to my boss at Eggy for writing this. Thanks, Vivian Liang. And then we'll change it to look like this. So we'll still have an order service, which gets called by our web client, but instead of the payment and delivery service getting called synchronously, we'll write an event to Kafka. So then we'll have a payment and a delivery service that each read from Kafka and do their own work. And we're going to call them workers to emphasize so they don't take synchronous calls. Is this working? Is this working at all? I'm not sure. Who knows? Okay, so we are going to try to run this distributed system on my computer, a 2014 Mac, which hopefully will run all of this and also Zoom quickly. Okay, so this is our demo code repo, which you can see on the internet later. And each of our services is a folder in this Go directory. And so each of these main.go files compiles into a binary with Bazel. And here in Protos, you can see our service definitions for each of these services. So the order service, which is the one that gets called by the web app, let's leave this guy here, has a create order RPC. The payment service has a process payment RPC. The delivery service has a deliver order RPC. And in the logic for the order service, we call process payment and deliver order synchronously, and we return successfully only if both are successful. So let's see if this works. Let's try to run them. Let's see. This guy, oops, wrong version. Let's run this one, synchronous. Okay, order sync API, payment API, delivery API. Let's run you. And then let us go to the web app. Order. The code for this is also in the example repo. The whole thing in theory should be runnable. And this is being served with Node over here. Okay, let's say that we want, what can we choose? Let's say we want an egg and a pancake, maybe lots of pancakes and some baguettes. Sorry, this is a weird breakfast. And let's check out what's going on in the console. Okay, let's place our order. Okay, our order is on the way. Okay, so we can see what's happening in our services. Order API got it, called payment API and delivery API, everything's good. And now let's say we would like some more breakfast. So order more breakfast. Okay, let's say that we're having some iffy network or something like that, and our payment service is only intermittently available to our order service. Let's emulate that by terminating it. Okay, and let's try again here. Let's see, what do I want for breakfast this time? I only want potatoes. Lots of potatoes. Okay. Not sure why. Okay.
Too many carbs. That's why.
Now I cannot get them because, oh yes, there is an error from payment API. Okay, the order service can't reach the payment service for a minute and I cannot get my potatoes. Where are my potatoes? No potatoes. Okay, so that is fine. We've noted what the behavior is in different cases with our synchronous request response service. Now let us, do a re-architecture toward an event-driven mechanism. So before, will it render both of these at the same time? Nope. Okay, so previously we had this setup where we had a synchronous service call to other services synchronously, and now we're going to have the order service write to Kafka and have the payment and delivery workers read from Kafka and do their own work separately from each other. So let's read the code for that. Sorry, this is a little hard to follow, but you can see in the order service now that instead of calling the services synchronously, we are writing the fact that we've produced the order to Kafka and firing that and forgetting it. And in the workers, we are just consuming from Kafka. So there's just this loop that handles what's going on. And okay, let's try to run this and see if it works. Here is Kafka running in Minikube, maybe. Let's see if this works. Okay, so we have our services. This is our async version. And now let us see if this works. Not really. Oh. Let's see. Maybe my hypervisor broke. Oh, yeah. Okay, maybe we can do jokes for 1 minute.
Daniel, hit the joke button, Daniel.
I don't think I have that button.
It's funny. I think every meetup, we should have told you this, Melinda, every meetup just about there's a demo problem.
You didn't tell me that earlier.
I'm sorry, I didn't want to jinx it.
Never
this is fantastic, by the way. You've run a master class on a technical presentation. It's been fantastic so far.
Oh, thanks so much.
Those of you in the audience, if you have any questions, get them in that QA section. Please do.
Wilson keeping up the tradition. Yeah.
See.
Sure.
Exactly. Years in sales engineering, and it's always you check the demo the night before, you check the demo the morning of, you check the demo just before the presentation, and it still goes wrong. It's just how demos are.
So good.
It's hard to run Kubernetes.
Yes, true story. True story.
So while we're
and Zoom at the same time. Let's see.
I'm working hard here to try to fill in the dead space. So hey everyone, if you haven't signed up for our next event, I am putting it here in the chat. Sign up or I'll have to come hunt you down. Thank
you, Jim. I appreciate that joke. That is straight out of vaudeville. That's perfect.
Oh, Jim. Oh, hello, Jim.
Yeah. So I'm gonna read this one out loud because I don't think everyone can see what Jim wrote. But first of all, Jim, good to see you. When my wife told me to stop acting like a flamingo, I had to put my foot down. I'm here all week, try the veal. Yeah.
That's really quite good.
Yeah.
That is actually, Jim. Thank you for the PG joke. Appreciate that. Clean around here.
All right, let's see if you're gonna work now. No.
Yeah. One question coming in, two questions coming in from, I'm gonna guess Kaya Kaya or Kaha Kaha. I don't know which language we are referring to there. So however to pronounce the J.
So maybe try to answer some questions. Can you work on that, Melinda, and answer questions at the same time?
I would
Oh
say.
yeah, for sure. I'm just waiting.
Oh, okay.
You know, it's trying to spin up a DVM here. That's all.
So Kaya Kaya wants to know, when the payment service comes back, it is going to process the event again. So should there be an expiry time for these messages so it doesn't process, offline or out of order or something along those lines?
Yeah. So in the asynchronous version that we saw already, the payment service is not going to process the event once it comes back online. Right, the only part of the demo that has worked so far. However, yeah, to your point, in the event-driven system, we will have the payment worker reprocess the message when it comes back, if it, for instance, it becomes dead. The idea with Kafka, and one of its great benefits, is that events are totally ordered. We're guaranteed a total ordering of messages across any single topic partition. And so that tends to be a good thing, that our messages will get reprocessed. There are different ways of doing event-driven architectures. There are message brokers that would do have expertise on them, something that's more akin to, say, an AMQP based protocol or SQS. Tends to be a little bit of a different use case. In this use case, we do want to guarantee that every message does get reprocessed. Let's see if the JVM came up, maybe. Because while we don't need to guarantee that the payment API processes something successfully synchronously, we do want to make sure that the person pays for their breakfast. So yeah, we want it to exist and be a good thing. Okay, I guess it just deleted my entire cluster here. Yep. As one does.
Another question we have coming in from the chat is, what are the latencies to look out for in pub sub communication? And also, I've been informed that the J in Kaja is as John. So Kaja, it was naturally one of the 20 ways of pronouncing J that I didn't pick. So there you go.
Got it. Could you say that one more time? Sorry, it cut out a little bit here.
Right. I'm trying to do only 4 or 5 things at once. So what are the latencies to look out for in pub sub communication?
Yeah, for sure. So yeah, we are moving from synchronous to asynchronous architectures at this point. So we are moving from real time. Sorry. We are moving from real time to, we are moving from real time to near real time processing. So there are different ways that you can tune these things. So Kafka in particular, which, if you can tell, I love and use heavily, even when it is not really working for me in my demo, has many different timeouts that you can tune. So you can tune how long the consumer will hang on to messages before it sends them up as a batch. You can tune. So basically, you're trading off throughput and latency. It depends on your use case. So there are many timeouts. Basically, it's very configurable. There are many timeouts depending on how close you want something to be to real time versus how much throughput you want to get. Yeah, you would choose something different. Depends on your context. Sorry, do you mind if I try to actually show the rest of this demo?
Do your thing. Yeah.
Okay. So sorry. Sorry for that. We are, again, trying to show this asynchronous order service. So we are ordering some potatoes, I think, maybe. Let's go back to our breakfast app. And okay, we have tried our potatoes and we now have received our potatoes. Okay, or we believe our potatoes are on the way. The user-facing behavior, basically in this case, what we're trying to show is that the user-facing behavior is the same as it was before in the success case, which is expected when everything is going well. As was pointed out, there is some latency in this pipeline, but it is, well, our timeouts here are tuned to be pretty fast. Yeah, in the success case, async and sync are basically the same. But let's say, just like before, we're having an iffy day, happens, and our delivery worker is going up and down. So let's emulate that by terminating it. And then let's see, let us try again. This guy, what do we want to order for breakfast now? Let's say this time we just want an egg, maybe. Okay, also some pancakes. Sorry, this pancake emoji is very delicious. Okay. And so even though the delivery worker is down for a moment, this succeeds. And that's because, as we said before, we want to guarantee that these messages do get processed. And so when this worker starts up again and connects, it should catch back up and process the order that it missed. So this user-facing behavior is quite different from the synchronous one.
Cool.
Let's see what this looks like if we want to add one more piece of functionality. You know, really pushing it here. Let's say that we want to send users a push notification if they order breakfast, so they aren't informed only by this web app with this delicious photo of brown sausage. So we posit that this should be a fairly straightforward operation. We can just add another worker that's consuming from this same topic, right? Okay, let's try it. Let's try it. Oops.
You got this.
Okay. Events. Okay, well, this one I just added like half an hour before the talk, so I'm not sure if it's going to work. Sorry in advance, but let's see. Okay, so we now have some code about push notifications, and let's do workers, push notifier, and let us, what is this, edit session. While it's building, name it, so we don't forget who it is. This is very laggy, sorry. I'm bright. Okay. Maybe. Sorry, it's compiling a lot of stuff about push notifications right now. But let's take a look at the code while it's doing that. Okay, I guess it compiled. Just like before, here's another directory for the push notifier. Here's another worker. And let's do another order. Order more breakfast. Okay. Bones? Only bones. Okay, that's a bad breakfast, actually. Let's try something different. Let's order one. Okay, let's order an actual delicious breakfast. An egg, a pancake, and a potato. Please send breakfast. Oh, let's see. See if I have anything embarrassing on my phone before I do this. Okay, let's see. Please send breakfast. Okay, oh, you can't see my screen. Oh, maybe you can see my screen. Maybe I need to stop sharing my screen, but you can see that breakfast is on the way. Yeah. Okay. So I will stop talking now that I have taken way too much time. Sorry.
You took the correct
I
amount of time, in fact. So then we do have one more question. And of
Okay.
course, that was awesome. That was really cool. But we have one more question from Jim. So that was our joke supplier here. What do you find is the best way to monitor and identify problem areas in the event-driven system, as in messages backing up and so forth? He mentions New Relic or the like, and then he also says as a follow-up, what do you find is the best metric for scaling, for example, queue length?
Yeah, for sure. I mean, that's a huge thing. I mean, the reason why all of these things exist, and we have Lightstep and all of these other solutions, is because we really just need to understand what's going on. For monitoring, I think the biggest metric that, in my experience, the metric that I found in my experience to be the most helpful is consumer lag. So topics in Kafka or distributed logs, they're a little different than queuing systems like SQS or RabbitMQ or something like that, where the topic is stored regardless. The events are stored regardless, right? Somebody consuming the message disappear from the broker. And so we don't really have queue lengths in the exact same way as we would in another queuing system. But consumer lag would be the equivalent in this case. So every consumer of a Kafka topic partition stores an offset of where it is, how far it's gotten. And that offset could be close to the tail of the log, or it could be really far behind, depending on how slow it is or where it started. And so the difference between its offset and the tail is the consumer lag. Sorry, you probably all know all of this. Those are things that I find helpful both. So tracking consumer lag both in time, like the actual clock time of the latest message timestamp versus the latest message timestamp that we've consumed, or in total number. And in so in our monitoring systems, we'll typically show consumer lag for each of these consumers. There are other metrics, like we care about throughput, we care about how long how long it takes to process each message. But really, if you look at the lags, that will tell a lot of the story.
Mhm. We have just about 3 minutes left. So I don't know if we have any more questions from the audience. I don't see anything in the chat or in the Q&A. Let's see. Okay, well, one of the questions that I thought people would ask that they didn't, we saw a couple of places where request and response coexisted with distributed events. And I was curious for your criteria in determining which is appropriate for a scenario.
Yeah, for sure. I think in general, we do use both, right? I do personally have a hypothesis that once event-driven systems become the norm, or if event-driven systems become the norm on the back end, that because event-driven systems are common in all other parts of our stack, that we'll see a full event-driven pipeline where your web browser, your web client will subscribe to changes in your database, basically. I think it's a little antiquated, the model that we have now of you're just seeing stale information on your screen for the rest of your life until you hit refresh. But for now, before we have that unification, usually the layer that talks to the clients ends up being request response. There are cases where you do want that synchronous binding, right? Like we want things to be loosely coupled, but we need things that need to go together to still go together, right? And that's one of the lessons from this monolith to microservices migration too, right? Sometimes things are coupled and maybe they should just be the same service, or at best or worst, have synchronous calls. There are different patterns around maybe having like an asynchronous core where you store most of your data, but then having edges of synchronous services. There are lots of different patterns with this. It really does depend on the context, which I realize is a bad answer to all of these things, but
That's the most computer
true.
science answer possible. It depends. Yeah. Well, we are just about out of time, so let's call it there.
Daniel, hold on, Daniel. We have a couple questions in the Q&A box. Maybe just check that real quick.
Yeah, but we're out of time. We can't keep people over like that.
Okay. I was mesmerized. You have to, Melinda, you have to tell us, how did you do those slides? We got several comments that they are the best slides they've seen. What's your secret?
Oh, that's really that's really I think love and care for Kafka perhaps, but there's an app on the iPad called Paper. It primarily makes these nice little watercolors.
That's
Yeah,
very cool.
I would recommend it.
Great. And you did that yourself?
Yes.
That's even more impressive. Fantastic. Well, thank you everybody for being here. Melinda, thank you so much for putting the time together and presented to us. It's been one of the best presentations that we've had by far. And we'd love to have you come again. And thank you, Daniel. Appreciate the hosting. And I do want to just share, if I can. Just want to, so this is our next event, everybody. That's mark your calendar. It's May 26th. And yeah, so we'll see you then. It's great to see some familiar faces. Jim, thanks for the joke. We needed that. Will, thanks for the questions, and hope to see everybody soon. And Melinda, we'll be talking soon. Thank you, Melinda. Take care now.
Sweet. Thank you all so much for your time. This was a blast.
Awesome. Thank you. Take care. Bye.